Hi, welcome to another video. Today we're going to talk about two types of nuclear reactions called fission and fusion. The goal today is to be able to describe the differences and similarities between fission and fusion, basically to compare and contrast them. We're going to go over a nuclear equation again with the do now, do our notes on fission and fusion, and look at a few examples of fission and fusion out in the real world. I would like you to complete a Venn diagram comparing the two, and we'll do some practice questions. So here's a typical part 2 question. Complete the nuclear equation below for the decay of cesium-137 by writing the notation for the missing product. Any chemical equation has to conserve mass, charge, and energy. So if we take a look at this, our missing product is going to have to conserve our mass. So we have 137 AMU is our mass on the reactant side. An electron has no mass, which means our mass number is going to be 137. We have a total of 55 on the reactant side. We need a total of 55 on the product side. 56 minus 1 is going to get us 55. That means we're going to have to look up element number 56, and the final answer is barium-137. So the first reaction we're going to go over is fusion. So fusion very much is what it sounds like. It's two things coming together or fusing together. So we have two or more light nuclei combining to make a single nucleus of greater mass. So two or more things fusing together to make a larger nuclei. This is considered an artificial transmutation. This doesn't naturally occur on Earth. It requires extreme amounts of heat and pressure and produces a greater amount of energy than fission. It also has no radioactive waste, which is a positive of fusion reactions. The way I like to remember fusion is it does naturally occur on the sun. So even though it's considered an artificial transmutation, it's artificial on the planet Earth, but this is what's happening on the surface of a star. So fusion typically occurs again with two small nuclei. Typically hydrogen are smallest nuclei. They combine to make a large amount of energy in a larger nucleus, and it's imperative that you recognize the equation for it. So we have two hydrogen atoms making one larger helium atom plus a large amount of energy. So again, you need to recognize this equation. And again, the way I remember this is fusion. It has a U in it. It's happening on the sun, which also has a U in it. And typically stars are made of basic elements like hydrogen and helium. Our next nuclear reaction that we're going to look at is fission. Fission is also an artificial transmutation. Artificial transmutation, once again, on the planet Earth require a particle accelerator. This is where a neutron is required to hit a heavy nucleus, usually uranium-235 or plutonium-239. When the neutron hits one of these heavy nuclei, it produces smaller nuclei and some energy. It produces a great amount of energy, but it also produces radioactive waste and free neutrons. The radioactive waste is definitely one of the cons of fission compared to fusion. And this is what it's going to look like. So you're going to have a neutron hitting a large nuclei, again like uranium-235, and it's going to cause that unstable nucleus to break apart into many other more stable pieces. So again, it's going to transmutate into more elements, it's going to produce more neutrons and a great amount of energy. This is another equation that you need to recognize, so please write it down. But you're really looking for uranium-235 or plutonium here, plus a neutron as your indicator that it's a fission reaction. So fusion occurs on the sun. Here's an example of where fission is occurring. Atomic bombs, such as those used in World War II, have uncontrolled fission reactions that are used in our weapons, like the atomic bomb. Nuclear power also uses controlled fission reactions to produce energy, such as Indian Point, which is our nearest nuclear power plant. Controlled fission reactions, again, yes, they produce energy, but they also do produce radioactive waste, which then have to be cooled continually and dealt with, as in transported somewhere to store for long term. One last phenomena that I want to go over is called mass defect. Mass defect is when a small amount of mass is lost during a nuclear reaction and converted to energy. So just like I've been saying repeatedly in the last couple of videos, mass, charge, and energy are conserved. That does not always mean the mass stays exactly the same, and this is specific to nuclear reactions. So during fission and fusion, products end up with less mass than the reactants because mass has been converted to energy. This is why fission and fusion both make large amounts of energy. What I would like you to do is now to summarize the video in your notes into a Venn diagram. That's when you have the two overlapping circles comparing fusion and fission. Here's what my Venn diagram would look like and some of the key points I would include. The biggest one in terms of similarities is that they both make a lot of energy. Fission, big difference is it's splitting atoms, whereas fusion is bringing atoms together. Fusion happens all over the surface of the sun and other stars, but it's artificial transmutation in terms of on Earth, so is fission, so that could be another similarity that you add in the center. But basically, here are your key points. If you have any questions, please let me know. Otherwise, have a wonderful day.